Current energy production methods rely on depletable sources such as fossil fuels. These reservoirs are finite, calling for a renewable, more sustainable source of energy. Additionally, in the past year, energy prices have increased by 86%. To help solve the ever-increasing demand of energy, we have come up with a possible solution. Small hydrogen gas-producing bacteria such as E. coli might be the answer. These tiny bacteria can convert carbohydrates from biomass waste into valuable hydrogen gas. Hydrogen gas, the chemical formula being H2, is a very promising prospect in the domain of green energy, as it is an excellent energy carrier. All that while producing significantly less greenhouse gases than current methods such as thermal-chemical production of hydrogen. There are multiple ways to use bacteria to produce H2, like using photofermentation and biophotolysis. We chose dark fermentation because it uses waste, solving another environmental issue. We will guide you through the steps of the dark fermentation reactions where glucose is ultimately converted to hydrogen gas and other waste products. The general reaction is as follows. Organic waste is fed to E. coli in an anaerobic environment. This video will focus on the processing of glucose within the bacteria. This is generally a 5-step process involving 3 main enzymes: pyruvate formate lyase, formate dehydrogenase, and the most important one, hydrogenase. All in all, this reaction produces 8 hydrogen molecules per molecule of glucose. This is a ratio of 16 hydrogen for 6 carbon. Firstly, glucose is converted to 2 pyruvate molecules in a process called glycolysis. These pyruvate molecules are then turned into 6 formate molecules by pyruvate formate lyase, PFL. NADH molecules are produced during the conversion. These will also be used to create hydrogen later on in the process. Formate dehydrogenase splits into CO2 and hydrogen through the oxidation of formate, producing 2 electrons. Formate dehydrogenase takes these electrons and transfers them to hydrogenase. This enzyme turns these electrons together with protons into hydrogen molecules. This step produces a total of 6 hydrogen molecules. Remember the NADH from the first step? Well, these molecules are oxidized to NAD+, as they transfer their electrons to reduce ferredoxin. Ferredoxin then transfers these electrons to hydrogenase, which combines them with nearby protons to create 2 hydrogen molecules. As you can see from the emission of CO2, this reaction is not 100% green. However, using waste as starting material also contributes to the development of a circular economy in that it reuses waste products. This method therefore alleviates some of the current energy problems in a semi-sustainable way.